So as we tend to do in AP Physics, we generalize our results to apply to a more robust spread of possibilities. So we're going to consider motion along a curved path and then vary the force as well as the path. The path will be varying in direction and the force will be varying as well. So how do we handle that? It's not too difficult. Consider a path from P1 to P2. And at some intermediate points here, we have a differential part of the path. So this path is continuous, of course, from P1 to P2. At any given point, I'm choosing this one right here, we're taking a differential length of this path. So, of course, this little differential is way too long, but it's in the direction of the path, and it's infinitesimal in size, always tangent to the curve. All right, so now the force right at this point, right at this moment, over the interval of dl is as given. So the force, we know actually from this particular curve that the force would have to be underneath the inside of the curve. And here's theta, or phi, which is the angle between dl, the direction of the motion at that moment, at that point, and the force. So that's phi. So this is the perpendicular part of that force, which is radial at that point, and that's f sine of phi. And then we have f parallel, which in this example is cosine of phi. So don't get that mixed up with our analysis of inclined planes, which flips that around. So you're looking at the situation. So the parallel part, f cosine, perpendicular part, f sine. The differential work, the work done over that differential interval, dw, is simply the product of those two things, f cosine of theta, of phi, sorry. So it's the parallel, the part of the force in the same direction as the path. So that's f cosine of phi dl. That should look familiar. That's f dot dl. It's a scalar dot product. So now we can specify the total work done on an object and moving it from point P1 to P2. Doesn't matter what the object is, makes no difference, because we are just specifying the force and the direction at any given point. So it's the integral from P1 to P2 of the f cosine of phi dl. That's just the integral of dw, really. So we're integrating dw, coming up with total work. And that can be simplified to f parallel dl, or more precisely, the total work is integral from P1 to P2 of f dot dl. Now this result that we ended up with is called a line integral. It appears now, we'll use it, and also it will be something that will surface when we get to E and M, so stay tuned for that. Now let's do an example or two utilizing this concept. Let's check out this interesting problem. We have a swing. Here's the chain represented. And you're going to push your little brother on this swing with a horizontal force. There he is. And we got an angle theta here, a radius equal to r, and here's your horizontal force. You're always pushing with a horizontal force. You're going to do it in such a way that you don't produce an acceleration. So you just push to the right horizontally with whatever force you need to keep moving him along the path that he then subsequently moves on, which is this circular path here. That's the path that he's going to move on. At the point in question right now, here's a perpendicular to the chain. This is the direction of the force. So this is the direction of dl, and there's your theta, the angle between those two. So there's dl. dl a little bit later, obviously in a different direction. So we got to figure out the total work done on the kid brother. The work done by the chain, or the chain set of the swing set. What's the work done by this, chain? And then the work that you do applying force F. Now, free body force diagrams are pretty important. So here's mg acting on the kid, the applied force, the tension of the chain, and with the vertical, that's also phi, alternate interior angles here, theta. And so we have t cosine of theta. That would be equal to the weight, right? If there's no acceleration vertically. And we have t sine of theta, which is going to be opposing your force. So these are equal, or there'd be a horizontal acceleration, which there is not. So sum of the forces is 0, no acceleration. Work total on boy, therefore, is really F net total times displacement, which is 0, or total change in kinetic energy, which is 0, because he starts and ends with change in speed. Now, the tension, this tension force, the tension of the chain pulling on the buoy, it's always perpendicular to the path itself. And you know what that means. The work done by the chain is 0. As the line integral would show you, if we integrate the tension through dl across the entire path, then they're always, every instant, dl and the tension are perpendicular. So now we've answered 2 of the questions. Total work done, 0. Work done by the chain, 0. The interesting part is, what is the work done by you in pushing it? Because you can see there's a displacement in that direction as well. So what is the work done by the force F? So we want to find the work done by F. Here's the free body diagram. So let's develop this a little more. Recognizing that the sum of the forces in the x is 0. So t sine of theta equals F. So sum of the forces in the y is 0, meaning t cosine of theta is mg. Bring those together. Actually, divide both of those equations. T sine over t cosine is F over mg. That's tangent of theta. Therefore, the force is mg tangent of theta. That's the force. The force is with respect to theta. And in fact, that's consistent with how we need to do the math. We need to integrate this with respect to theta, not L. I mean, L is changing directions, and it's kind of a funny variable that's not easy to work with in this context. But we can transpose. We can convert the dl into d theta as follows. We know arc length, S, is equal to r theta. And dl then, the differential length, is really the magnitude of ds. So the little arc length. Same thing at the differential level, right? And magnitude of ds is r d theta. So we've just made the transition from dl to d theta by multiplying by r. So work done by the force is equal to the integral of F dot dl. And let's carry this out. Work done by the force, integral of F dot dl, which is integral of F cosine of theta dl. That's what the dot product is. And that is F cosine of theta ds, because dl became ds. Now, the force we just saw is mg tangent of theta, so that's the F. We're going to multiply that by cosine of theta. And then what was ds? Well, ds was r d theta. So there we go. There's the whole thing. Now let's simplify that. We can bring out the constants mgr. Integral from 0 to theta, those are the limits with our differential theta. We're going to evaluate this from 0 to the angle in question that the swing travels through. Tangent, sine over cosine. Cosine goes away, you end up with sine. Sine is minus cosine. And so we have mgr times cosine of theta minus 1. The minus in front of the whole thing. And there is our result that we're looking for. mgr times 1 minus cosine of theta. And it turns out that that's also equal to just mgh. R times 1 minus cosine of theta is just the height. So if you grab your kid brother and lifted him straight up to that height, you would do the same amount of work. Interesting thought, though. It's very different in detail because you're pushing with this horizontal force. Remember the original drawing, that horizontal force. And think of getting him up to 90 degrees. What kind of force would it take to get that swing horizontal. And if you think through that, you'd have to conclude that the force would progress toward infinity. So you would be approaching an infinite force to the right, but as you approach that infinite force to the right, the displacement to the right is approaching 0 at the same time. So that's the limit of the reasonability for this thing. So you're approaching infinite force with 0 displacement, and it turns out that the total work done is still just mgh.